Hello, and welcome to Lumos Laboratory. In this video, I'll be summarizing what I learned in week 2 of my first semester of my third year program. Check the description for more information. In the lecture, machine learning was introduced. Supervised learning gives both question and answer. Unsupervised gives only question. Reinforcement gives questions and answers intermittently. Classification splits answers into categories, while regression has real-valued answers. Data can be visualized with histograms for one parameter, or scatter plots for two parameters. A decision tree is a primitive categorizing algorithm that repeatedly splits the set of possible inputs using a straight line through one parameter. One can increase the depth for more precise results, but be careful of overfitting. Multiple trees can be combined through boosting or averaging to achieve better results. We may solve ordinary differential equations in a variety of methods. The simplest is direct Euler, which uses the slope at the current point to predict the next. We may decrease the step size between points to increase precision, but increase computation time. Runge-Kutta methods repeatedly recalculate the slope at the midpoint in order to have a better approximation, with only a little more calculation than direct Euler. As one increases the order of Runge-Kutta, it improves the accuracy in a general case. However, there are cases where the Runge-Kutta performs as poorly as direct Euler. The first law describes changes in energy summing to heat and work. This may be used when deriving a variety of results, including relationships between specific heats for constant volume and pressure, and the effects of reversible isothermal, reversible adiabatic, and irreversible adiabatic expansions. The Carnot engine is a cyclic process of moving heat by doing work. Clausius stated that an ideal refrigerator cannot exist, and Kelvin and Planck stated that a perfect engine cannot exist. These statements are equivalent. They also show that an engine cannot be more efficient than a Carnot engine. Somehow, temperature definitions are unified. Systems of particles work similarly to independent particles with macroscopic definitions of mass, position, momentum, angular momentum, and energy, having similar or identical consequences due to Newton's laws. Corrections are needed when working with frames moving relative to center of mass, but still lead to similar results. Rotating frames, since not inertial, produce greater problems and break Newton's laws, with extra centrifugal and Coriolis forces. Reviewing matrices. Addition works as expected. Square matrices have a trace. The transpose flips the matrix, and the product is a tad complicated. Determinants have many properties and can be calculated recursively or with Levi-Civita for 3x3 matrices. Orthogonal matrices have orthonormal vectors as rows or columns, and their transpose is the inverse. True tensors are invariant under all transformations, while pseudotensors invert under improper transformations, such as inverting the basis. Pseudovectors and pseudoscalars are examples, with pseudovectors often being formed by a cross product. We can represent the states of a system as vectors in a Hilbert space. For example, a two-state system would have one basis vector per state. A more complicated system may be derived as a tensor product of its components. Observables, outcomes of measurements in real life, produce stochastic variables. States are wave functions which describe the probabilities of any one outcome. We may assign a unique operator to observables. Possible outcomes are eigenvalues, and states are linear sums of eigenvectors. We will work with Hermitian operators, i.e. equal to their own conjugate, since they have these properties. Consider curves in Euclidean space, a map from real numbers t to points in space represented by vector x of t. Consider these formulas. T is a unit tangent vector. Reparametrization allows enforcing unit speed. This conveniences calculating curvature and torsion. Curvature requires non-zero speed, and torsion requires non-zero curvature, which combined make a curve biregular. The Frenet-Serret frame uses the tangent, normal, and binormal vectors to find a basis on any point on the line. Curves may be transformed, Euclidean transformations preserving curvature and torsion. Thus, if two curves share them, they must be a Euclidean transform apart.